Part 2, Chapter 1 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy During the 19th Century by Agnes Mary Clerke. Chapter 1, Foundation of Astronomical Physics, Part 2. Convincing evidence as to the true nature of the solar lines was, however, at length, in the autumn of 1859, brought forward at Heidelberg. Kirchhoff's experimentum crucis in the matter was a very simple one. He threw bright sunshine across a space occupied by vapour of sodium, and perceived with astonishment that the dark Fraunhofer line D, instead of being effaced by flame, giving a luminous ray of the same refrangibility, was deepened and thickened by the superposition. He tried the same experiment, substituting for sunbeams light from a Drummond lamp, and with similar result. A dark furrow, corresponding in every respect to the solar D line, was instantly seen to interrupt the otherwise unbroken radiance of its spectrum. The inference was irresistible, that the effect thus produced artificially was brought about naturally in the same way, and that sodium formed an ingredient in the glowing atmosphere of the sun. This first discovery was quickly followed up by the identification of numerous bright rays in the spectra of other metallic bodies with others of the hitherto mysterious Fraunhofer lines. Kirchhoff was thus led to the conclusion that besides sodium, iron, magnesium, calcium, and chromium are certainly solar constituents, and that copper, zinc, barium, and nickel are also present, though in smaller quantities. As to cobalt, he hesitated to pronounce, but its existence in the sun has since been established. These memorable results were founded upon a general principle first enunciated by Kirchhoff in a communication to the Berlin Academy, December 15, 1859, and afterwards more fully developed by him. It may be expressed as follows: substances of every kind are opaque to the precise rays which they emit at the same temperature. That is to say, they stop the kinds of light or heat which they are then actually in a condition to radiate. But it does not follow that cool bodies absorb the rays which they would give out if sufficiently heated. Hydrogen at ordinary temperatures, for instance, is almost perfectly transparent. But if raised to the glowing point, as by the passage of electricity, it then becomes capable of arresting and at the same time of displaying in its own spectrum light of 4 distinct colours. This principle is fundamental to solar chemistry. It gives the key to the hieroglyphics of the Fraunhofer lines. The identical characters which are written bright in terrestrial spectra are written dark in the unrolled sheaf of sun rays. The meaning remains unchanged. It must, however, be remembered that they are only relatively dark. The substances stopping those particular tints in the neighbourhood of the sun are at the same time vividly glowing with the very same. Remove the dazzling solar background, by contrast with which they show as obscure, and they will be seen, and at critical moments actually have been seen, in all their native splendour. It is because the atmosphere of the sun is cooler than the globe it envelops that the different kinds of vapour constituting that atmosphere take more than they give, absorb more light than they are capable of emitting. Raise them to the same temperature as the sun itself, and their powers of emission and absorption being brought exactly to the same level, the thousands of dusky rays in the solar spectrum will be at once obliterated. The establishment of the terrestrial science of spectrum analysis was due, as we have seen, equally to Kirchhoff and Bunsen, but its celestial application to Kirchhoff alone. He effected this object of the aspirations, more or less dim, of many other thinkers and workers by the union of two separate, though closely related, lines of research: the study of the different kinds of light emitted by various bodies, and the study of the different kinds of light absorbed by them. The latter branch appears to have been first entered upon by Dr. Thomas Young in 1803. It was pursued by the younger Herschel, by William Allen Miller, Brewster, and Gladstone. Brewster, indeed, made in 1833 a formal attempt to found what might be called an inverse system of analysis with the prism based upon absorption, and his efforts were repeated just a quarter of a century later by Gladstone, but no general point of view was attained, nor, it may be added, was it by this path attainable. Kirchhoff's map of the solar spectrum, drawn to scale with exquisite accuracy, and printed in 3 shades of ink to convey the graduated obscurity of the lines, was published in the Transactions of the Berlin Academy for 1861 and 1862. Representations of the principal lines belonging to various elementary bodies formed, as it were, a series of marginal notes accompanying the great solar scroll, enabling the veriest tyro in the new science to decipher its meaning at a glance. Where the dark solar and bright metallic rays agreed in position, it might safely be inferred that the metal emitting them was a solar constituent, and such coincidences were numerous. In the case of iron alone, no less than 60 occurred in one half of the spectral area, rendering the chances absolutely overwhelming against mere casual conjunction. The preparation of this elaborate picture proved so trying to the eyes that Kirchhoff was compelled, by failing vision, to resign the latter half of the task to his pupil Hoffmann. The complete map measured nearly 8 feet in length. The conclusions reached by Kirchhoff were no sooner announced than they took their place, with scarcely a dissenting voice, among the established truths of science. The broad result, that the dark lines in the spectrum of the sun afford an index to its chemical composition no less reliable than any of the tests used in the laboratory, was equally captivating to the imagination of the vulgar, and authentic in the judgment of the learned. And, like all genuine advances in the knowledge of nature, it stimulated curiosity far more than it gratified it. Now, the history of how discoveries were missed is often quite as instructive as the history of how they were made. It may then be worth while to expend a few words on the thoughts and trials by which, in the present case, the actual event was heralded. 3 times it seemed on the verge of being anticipated. The experiment, which in Kirchhoff's hands proved decisive, of passing sunlight through glowing vapours and examining the superposed spectra, was performed by Professor W. A. Miller of King's College in 1845. Nay, more, it was performed with express reference to the question, then already, as has been noted, in debate, of the possible production of Fraunhofer's lines by absorption in a solar atmosphere. Yet it led to nothing. Again, at Paris in 1849, with a view to testing the asserted coincidence between the solar D line and the bright yellow beam in the spectrum of the electric arc, really due to the unsuspected presence of sodium, Léon Foucault threw a ray of sunshine across the arc and observed its spectrum. He was surprised to see that the D line was rendered more intensely dark by the combination of lights. To assure himself still further, he substituted a reflected image of one of the white-hot carbon points for the sunbeam, with an identical result. The same ray was missing. It needed but another step to have generalized this result, and thus laid hold of a natural truth of the highest importance. But that step was not taken. Foucault, keen and brilliant though he was, rested satisfied with the information that the voltaic arc had the power of stopping the kind of light emitted by it. He asked no further question, and was consequently the bearer of no further intelligence on the subject. The truth conveyed by this remarkable experiment was, however, divined by one eminent man. Professor Stokes of Cambridge stated to Sir William Thomson, now Lord Kelvin, shortly after it had been made, his conviction that an absorbing atmosphere of sodium surrounded the sun; and so forcibly was his hearer impressed with the weight of the argument based upon the absolute agreement of the D line in the solar spectrum with the yellow ray of burning sodium, then freshly certified by W.H. Miller, combined with Foucault's reversal of that ray, that he regularly inculcated in his public lectures on natural philosophy at Glasgow 5 or 6 years before Kirchhoff's discovery, not only the fact of the presence of sodium in the solar neighbourhood, but also the principle of the study of solar and stellar chemistry in the spectra of flames. Yet it does not appear to have occurred to either of these two distinguished professors, themselves among the foremost of their time in the successful search for new truths, to verify practically a sagacious conjecture, in which was contained the possibility of a scientific revolution. It is just to add that Kirchhoff was unacquainted, when he undertook his investigation, either with the experiment of Foucault or the speculation of Stokes. For C.J. Ångström, on the other hand, perhaps somewhat too much has been claimed in the way of anticipation. His optical researches appeared at Upsala in 1853, and in their English garb 2 years later. They were undoubtedly pregnant with suggestion, yet made no epoch in discovery. The old perplexities continued to prevail after, as before their publication. To Ångström, indeed, belongs the great merit of having revived Euler's principle of the equivalence of emission and absorption. But he revived it in its original crude form, and without the qualifying proviso which alone gave it value as a clue to new truths. According to his statement, a body absorbs all the series of vibrations it is, under any circumstances, capable of emitting, as well as those connected with them by simple harmonic relations. This is far too wide. To render it either true or useful, it had to be reduced to the cautious terms employed by Kirchhoff. Radiation strictly and necessarily corresponds with absorption only when the temperature is the same. In point of fact, Ångström was still, in 1853, divided between absorption and interference as the mode of origin of the Fraunhofer dark rays. Very important, however, was his demonstration of the compound nature of the spark spectrum, which he showed to be made up of the spectrum of the metallic electrodes superposed upon that of the gas or gases across which the discharge passed. It may here be useful, since without some clear ideas on the subject no proper understanding of recent astronomical progress is possible, to take a cursory view of the elementary principles of spectrum analysis. To many of our readers they are doubtless already familiar, but it is better to appear trite to some than obscure even to a few. The spectrum, then, of a body is simply the light proceeding from it, spread out by refraction into a brilliant variegated band, passing from brownish red through crimson, orange, yellow, green, and azure into dusky violet. The reason of this spreading out or dispersion is that the various colours have different wave lengths, and consequently meet with different degrees of retardation in traversing the denser medium of the prism. The shortest and quickest vibrations, producing the sensation we call violet, are thrown farthest away from their original path; in other words, suffer the widest deviation. The longest and slowest, the red, travel much nearer to it. Thus the sheaf of rays, which would otherwise combine into a patch of white light, are separated through the divergence of their tracks after refraction by a prism, so as to form a tinted riband. This visible spectrum is prolonged invisibly at both ends by a long range of vibrations, either too rapid or too sluggish to affect the eye as light, but recognizable through their chemical and heating effects. Now, all incandescent solid or liquid substances, and even gases ignited under great pressure, give what is called a continuous spectrum; that is to say, the light derived from them is of every conceivable hue. Sorted out with the prism, its tints merge imperceptibly one into the other, uninterrupted by any dark spaces. No colours, in short, are missing. But gases and vapours, rendered luminous by heat, emit rays of only a few tints, which accordingly form an interrupted spectrum, usually designated as one of lines or bands. And since these rays are perfectly definite and characteristic, not being the same for any two substances, it is easy to tell what kind of matter is concerned in producing them. We may suppose that the inconceivably minute particles which by their rapid thrilling agitate the ethereal medium so as to produce light are free to give out their peculiar tone of vibration only when floating apart from each other in gaseous form. But when crowded together into a condensed mass, the clear ring of the distinctive note is drowned, so to speak, in a universal molecular clang. Thus, prismatic analysis has no power to identify individual kinds of matter, except when they present themselves as glowing vapours. A spectrum is said to be reversed when lines previously seen bright on a dark background appear dark on a bright background. In this form it is equally characteristic of chemical composition, with the direct spectrum being due to absorption, as the latter is to emission. And absorption and emission are, by Kirchhoff's law, strictly correlative. This is easily understood by the analogy of sound, for just as a tuning fork responds to sound waves of its own pitch, but remains indifferent to those of any other, so those particles of matter whose nature it is, when set swinging by heat, to vibrate a certain number of times in a second, thus giving rise to light of a particular shade of colour, appropriate those same vibrations, and those only, when transmitted past them, or, phrasing it otherwise, are opaque to them and transparent to all others. It should further be explained that the shape of the bright or dark spaces in the spectrum has nothing whatever to do with the nature of the phenomena. The lines and bands so frequently spoken of are seen as such for no other reason than because the light forming them is admitted through a narrow straight opening. Change that opening into a fine crescent or a sinuous curve, and the lines will at once appear as crescents or curves. Resuming in a sentence what has been already explained, we find that the prismatic analysis of the heavenly bodies was founded upon three classes of facts. First, the unmistakable character of the light given by each different kind of glowing vapour. Secondly, the identity of the light absorbed with the light emitted by each. Thirdly, the coincidence observed between rays missing from the solar spectrum and rays absorbed by various terrestrial substances. Thus a realm of knowledge, pronounced by Morinus in the 17th century, and no less dogmatically by Auguste Comte in the 19th, hopelessly out of reach of the human intellect, was thrown freely open, and the chemistry of the sun and stars took at once a leading place among the experimental sciences. The immediate increase of knowledge was not the chief result of Kirchhoff's labours. Still more important was the change in the scope and methods of astronomy, which, set on foot in 1852 by the detection of a common period affecting at once the spots on the sun and the magnetism of the earth, was extended and accelerated by the discovery of spectrum analysis. The nature of that change is concisely indicated by the heading of the present chapter. We would now ask our readers to endeavour to realize somewhat distinctly what is implied by the foundation of astronomical physics. Just 3 centuries ago, Kepler drew a forecast of what he called a physical astronomy, a science treating of the efficient causes of planetary motion and holding the key to the inner astronomy. What Kepler dreamed of and groped after, Newton realized. He showed the beautiful and symmetrical revolutions of the solar system to be governed by a uniformly acting cause, and that cause no other than the familiar force of gravity, which gives stability to all our terrestrial surroundings. The world under our feet was thus for the first time brought into physical connection with the world's peopling space, and a very tangible relationship was demonstrated as existing between what used to be called the corruptible matter of the earth and the incorruptible matter of the heavens. This process of unification of the cosmos, this levelling of the celestial with the sublunary, was carried no farther until the fact unexpectedly emerged from a vast and complicated mass of observations that the magnetism of the earth is subject to subtle influences, emanating certainly from some and presumably from all of the heavenly bodies. The inference being thus rendered at least plausible that a force not less universal than gravity itself, but with whose modes of action we are as yet unacquainted, pervades the universe, and forms, it might be said, an intangible bond of sympathy between its parts. Now, for the investigation of this influence, two roads are open. It may be pursued by observation either of the bodies from which it proceeds, or of the effects which it produces, that is to say, either by the astronomer or by the physicist, or better still, by both concurrently. Their acquisitions are mutually profitable, nor can either be considered as independent of the other. Any important accession to knowledge respecting the sun, for example, may be expected to cast a reflected light on the still obscure subject of terrestrial magnetism, while discoveries in magnetism, or its alter ego, electricity, must profoundly affect solar inquiries. The establishment of the new method of spectrum analysis drew far closer this alliance between celestial and terrestrial science. Indeed, they have come to merge so intimately one into the other that it is no easier to trace their respective boundaries than it is to draw a clear dividing line between the animal and vegetable kingdoms. Yet up to the middle of the last century, astronomy, while maintaining her strict union with mathematics, looked with indifference on the rest of the sciences. It was enough that she possessed the telescope and the calculus. Now the materials for her inductions are supplied by the chemist, the electrician, the inquirer into the most recondite mysteries of light and the molecular constitution of matter. She is concerned with what the geologist, the meteorologist, even the biologist has to say. She can afford to close her ears to no new truth of the physical order. Her position of lofty isolation has been exchanged for one of community and mutual aid. The astronomer has become, in the highest sense of the term, a physicist, while the physicist is bound to be something of an astronomer. This, then, is what is designed to be conveyed by the foundation of astronomical or cosmical physics. It means the establishment of a science of nature, whose conclusions are not only presumed by analogy, but are ascertained by observation to be valid wherever light can travel and gravity is obeyed; a science by which the nature of the stars can be studied upon the earth, and the nature of the earth can be made better known by study of the stars; a science, in a word, which is, or aims at being, one and universal, even as nature, the visible reflection of the invisible highest unity, is one and universal. It is not too much to say that a new birth of knowledge has ensued. The astronomy so signally promoted by Bessel, the astronomy placed by Comte at the head of the hierarchy of the physical sciences, was the science of the movements of the heavenly bodies. And there were those who began to regard it as a science which, from its very perfection, had ceased to be interesting, whose tale of discoveries was told, and whose farther advance must be in the line of minute technical improvements, not of novel and stirring disclosures. But the science of the nature of the heavenly bodies is one only in the beginning of its career. It is full of the audacities, the inconsistencies, the imperfections, the possibilities of youth. It promises everything. It has already performed much. It will doubtless perform much more. The means at its disposal are vast and are being daily augmented. What has so far been secured by them, it must now be our task to extricate from more doubtful surroundings and place in due order before our readers. End of Part 2, Chapter 1, Part 2.